Okay, so welcome everyone. Today we are very happy to have Nathan Benjamin from Caltech. And today he's going to tell us about high dimensional operators for high dimensional CFTs.
Okay, thanks very much for the introduction. I'm very happy to be here. Actually, I grew up not so far from here. I grew up in Indiana, so it's very nice to visit Chicago. Thanks very much for the invitation. And of course, please feel free to interrupt me at any time. I hope it's very informal. So the title of my talk is High Dimension Operators for High Dimension CFTs. And actually the two meanings of high dimension are different, as we'll see. The first high dimension is going to be really heavy operators, but the second high dimension is just any conformal field theory and larger than 2 space-time dimensions. So 3 is already large. And this is based on 2 papers, one that appeared last summer with Jeha Lee, Hiroshi Oguri, and David Simmons-Duffin, and the second to appear hopefully in next month or 2 with Jeha Lee, Shurip Pal, David Simmons-Duffin, and Yixin Shu. And I should say that Jeha and Yixin are 2 very fantastic graduate students at Caltech. So let's, before we get into any of the technical topics of what I'm going to discuss in this talk, I'm going to ask a big picture question, which is what universal features do all CFTs share? So there are a lot of these known universal features, and maybe the most famous one of these universal features is in 2 dimensions. One answer is in 2D CFT, the entropy of a CFT. So the entropy of let's say the number of local operators of some dimension delta and spin j, provided the dimension is large enough, is universal. And this is a celebrated result known as the Cardian law. So I'll just write it here, just in case it's not familiar. So here I wrote it in terms of the total scaling dimension delta and the spin j. And Cardian showed in the 80s that regardless of whatever the details of your CFT are, at very high energies, the density of states takes a universal form, which just depends on a single parameter, the central charge, provided that the dimension, the spins, are much larger than the central charge. So this tilde here, I'll say more about later, but this says that roughly speaking, the errors are non-perturbatively small. So at very large scaling dimension, this is accurate to all orders in perturbation theory in 1/delta. And this is derived, Cardian derived this using from modular invariance, which states that the partition function of the CFT, the genus 1 partition function, is invariant under any large diffeomorphism of the torus, which is this group SL2Z. And from this formula, what you can do is there's one element of SL2Z is the so-called S transform. It takes tau and tau bar to -1/tau, -1/tau bar. So it's kind of like a high temperature, low temperature duality. You can take the partition function at very low temperature. The answer is universal. It's given by the vacuum state, which has some Casimir energy related to the central charge. You do this temperature to 1/temperature transformation. You do a Laplace transform, and you essentially get this formula on the nose. So this formula is valid for all 2D CFTs that are compact and unitary. You don't need to have large C. It's true for the Ising model. If you plug in C equals 1/2, and put it in Mathematica, you'll see that this is valid for the Ising model. But for holographic CFTs, so for theories dual to Einstein gravity in ADS3, there's quite a beautiful interpretation of this formula. So for the entropy, so if I take the log of this formula, this is the area of a BTZ per black hole. So of course this sort of had to be true. If this wasn't true, then ADS CFT wouldn't hold. But it's kind of a beautiful fact that some universal formulas on the pure CFT side is related to some universal formulas about black hole entropy in gravity. And the question that I would like to ask in this talk is, do such similar universal formulas hold in d bigger than 2 CFTs? One reason that you may expect the answer should be yes is that this second intuition, the AGS interpretation, is universal in higher dimensions as well. They're spinning Kerr black holes in ADS4 or ADS5, and they have some universal area just in terms of their quantum numbers. So it's reasonable to suspect that there may exist some universal formula here. On the other hand, this particular tool that we used, that Carter used to derive this formula is not available in higher dimensions. We're going to put the theory on SD minus 1 times S1, and so there's no natural SL to the acting on it. Doing something?
So SLD on the detour is just not that useful for.
Oh, very good. You could put the theory on some d-dimensional force, and you can then act with some SLD comma z or something, and you'll learn some very non-trivial information. But if you put this theory on this geometry, there's no operator state correspondence. So you won't you'll learn some very complicated information about the CFT, but you won't learn about the entropy of these high dimensional operators. But indeed, you could do this, and there have been a lot of interesting work studying that. But I'm going to be putting this theory on a cylinder. So in this talk, I'm going to show that the answer is yes. There is a universal formula for higher dimensions. There are going to be some caveats that I'll say later. I'll write some of them down now, which is that the 2D, the formula is non-perturbatively exact in 1/delta. But in bigger than 2D, there's going to be a series of perturbative corrections that'll describe exactly what they are. We also like to organize, into the larger symmetry. In 2D, of course, we have a Virasoro symmetry. We don't have this in higher D. We'll only talk about the density of global primers in higher D. And there's going to be instead of a single number central charge C controlling this density of states, there's going to be an infinite set of what I'll call Wilson coefficients controlling this density of states. So there are some caveats, but I'll go through all of these momentarily.
Is this phenomenon in 2D related to the fact that ADS3 gravity is one loop exact?
I actually don't. Oh, that's a good question. Let's see. I don't think so, because that's one loop exact in the central charge. That's one loop exact in C. And the analog of these numbers here, when I say it's non-perturbative, I'm doing an expansion in delta. So it may be related, but it's not obviously the same time.
Well, but delta is just the mass of the black hole.
But it could be much larger than C, for example. And you still have a fine solution.
But even the leading term and the thermal effective action could be different for different CFTs.
Yes,
So I don't know, why would we call that yes?
well, the leading term is like the central charge. The central charge is also different for.
No,
different
but we don't even know that term has to be there for when we put theories on.
Well, I think generically it will be there.
But generically is different than saying all.
Okay, let's say generically, yes. Okay, I'll get to this. So Clay jumping ahead, so I'll get there. And then we can debate how much the answer should be yes. You could also object to the answer yes because there's a large number of set of parameters, but the answer is quite functionally constrained. So maybe I'll get there. So as Clay foretold, the tool we'll use is called thermal effective filtering. And I should say, well, it may be older than this, but I first learned of this in a paper by Banerjee et al. From 2012.
Thermal effective filter was invented in 2012.
No. That's fine. Well, I learned of this technique. This paper explains it very nicely, but indeed, the idea for effective filter is much older. So what we're going to do is we're going to imagine compactifying our Euclidean CFT on a very, very small, long thin cylinder. So put it on an S1 of some length beta. And then we're going to ask what generic d-1 dimensional theory we get. And generically, we're going to get a massive quantum field theory. So put the theory on some S1 of length beta. We're going to get a gap d-1 dimensional quantum field theory, meaning that the operators at some long distance will decay exponentially. with some length scale c that's proportional to p by dimensional analysis. And we're going to view this gapped d-1 dimensional quantum field theory as a kind of modular dual. So in 2 dimensions, we put the theory on a circle, we essentially get back the theory itself. But here we're going to now consider this massive quantum field theory as a modular dual. And the idea is we're going to couple this d-dimensional CFT to some background gauge fields, and then write down an effective action as a function of these gauge fields. So let me say this in more detail. Is there like a preferred eraser, or is this the best? This is the
Try the other side.
on the other side?
No.
Sorry about this. No, it's okay. I already asked Shubhan for better talk, so I can't be greedy.
The problem is they wash the board, so we'll talk.
I see.
It doesn't
No
work
worries.
well.
So because we're compactifying on a circle, we can put this in KK form. We write the metric as d-1 dimensional metric. And we're going to say that the original CFT coupled to this background metric is a gap theory as a function of the metric, the gauge field, and the dimension. And the lore is that this gap theory is captured by a local effective action as a function of the d-1 dimensional fields. So this theory goes as e to the minus some s thermal as a function of the metric. And we're going to parameterize our ignorance of this d-1 dimensional theory in terms of an infinite set of Wilson coefficients in S thermal. So these Wilson coefficients will kind of play the role of the central charge.
Gap is associated to the temperature somehow?
Yeah, that's right. This math field is proportional to theta.
Oh.
The distance. Now the point is, symmetry is highly constrained what possible terms you can write down in the thermal effective action. So they constrain them in the usual way. First, we have d-dimensional coordinate invariance, which gives us a-1 dimensional coordinate invariance plus gauge invariance. But we also have Weil invariance of the original theory, which is the CFT. Weil metric is the same thing up to a Weil level. And what this forces is that you can't just have any combination of these G's, A's, and Phi's. In particular, it forces all combinations of the metric to appear in what I'll call this G hat, which is the combination of the dilettante and the metric.
You can also have naked contributions to the dilettante to make the anomalous effective action.
Sorry.
You can also have the dilettante appear separately to make the anomalous effective action.
Yeah, that's right. There'll be a term that to be in charge of the Weil number. That's right.
So, there's no strongly coupled zero-mode sector to worry about, or you're ignoring it, or?
Well, we're going to assume that the theory is gapped. So it could be that we land on a gapless theory, and I'll actually discuss some examples where this happens, like free theories or supersymmetric theories if you put a -1 to the f. But our assumption is generic, we're going to get a gap theory. That's an assumption, so that's part of this caveat of generically. So the final term for this thermal action that you can write down looks something like this. The d-1 dimensional theory. And I can write down an infinite set of terms. I can write down a cosmological constant, which I'll call negative. I'll call this negative for convenience, but I'll call this negative f. And then I can write down whatever terms that are consistent with these symmetries. So I can write down a Ricci scalar in terms of this G hat. I can write down a Maxwell term, and I can keep going. And then there'll be a Weyl piece, which takes care of the Weyl anomaly. What this will effectively do is provide some kind of Casimir energy shift of the energy. It's like this minus C/12 term in 2 dimensions. And these coefficients, I have C1, C2, and there's an infinite set of them. So I can write down any, any I can write an f to the 4th, or r hat squared, and I can kind of go wild. And each one of these Wilson coefficients will be one of these infinite set of parameters that determine sort of what the shape of these density of states look like. But as you'll see, they actually organize themselves very nicely in terms of a derivative expansion. So I'll say this more later, but basically what happens is that if you're only interested in some order in perturbation theory and 1 over delta, like let's say you're interested in corrections of the form 1 over delta squared, then effectively you only need to write down terms of up to like 2 derivatives in the effective action, of which there will only be a finite number of them. So if you're willing to tolerate a particular perturbative error, there's only like a finite number of terms you need to consider. Let me make an aside and ask, why is 2D special? Well, the first answer is the one I gave at the beginning of the talk, which is that in 2 dimensions, when you put the theory on ST minus 1 times S1, you have this is a torus, so you can use the magic of SL2Z. But from this effective field theory perspective, 2 dimensions is magic because in one dimension, I can't write down any of these higher derivative terms. So in 2 dimensions, this effective field theory truncates, and we just get a single term F, which will be related to the central charge. And this is why the 2-dimensional Cartier formula is accurate to all orders in perturbation theory, because you just can't write down these higher dimensional terms.
Can you say in effective field theory how to generate the exponentially suppressed corrections?
I don't think it's an effective field theory effect. I think this will be some like massive particles, like maybe massive ruled line instantons propagating. I think there could be some things to say about it. Like in each of these instantons, you could then write some effective action, but to say what the sort of perturbative corrections around the non-perturbative terms are, but I don't have too much more to say. For some free theories, we actually worked it out exactly, but these free theories are a bit subtle because of the zero mode and things like this. I can discuss this more afterwards.
Why can't you have terms like the gradient of this dilaton squared?
That's not gonna respect this combination. It won't respect the Allen
That's
E minus 1 equal to 3, do you have an ADA?
fantastic question. Yes, you can. You'll have this when the original CFT has some like gravitational anomaly. Similarly, in 2-dimensional CFT, we could have like an integral of the A term, and that'll be present if C left is not equal to C right in 2 dimensions. So maybe once I talk about the density of states, I'll say a little bit about that there. But yes, you can. In even dimensions, you can have some of these like Chern-Simons-like terms. So from this, let's extract the density of states. So let's keep the spin dependence. So we're going to put the theory on beta 1 times st minus 1, but we'll twist the angles on st minus 1. So what we're computing with this thermal effective action is z of beta and some omega, which is something we twist the sphere by, and what we're computing is this.
Does that correspond to a complex capital G,
G.
the metric? That's some metric.
Yeah. I don't think it's complex. It's just that when you go around the circle, you also have to twist the sphere by some corresponding angle.
It's a real metric.
I think it's a real metric. I think it depends on if this will make a real or complex. The way I predict it, I think it's real.
From a Lorentzian point of view, it's a complex metric.
Or Lorentzian point of view, it's a complex metric.
It's something that's first order in time, so when you wick rotate, it picks up an I. So to make it real again, you also have to analytically continue omega to imaginary values.
Okay, so what we do is we take this metric, we put it in inclusive time form, And then we just compute as many Wilson, as many of these terms as you want. And you'll get the approximation for the partition function. So let me say what the answer is. So this is approximately S thermal. And here's the answer. The volume of the sphere factor. So it looks something like this. The leading term is this cosmological constant term in the d-1 dimensional theory, and it scales like temperature to the d-1. This you could have read off just from some dimensional analysis arguments. But the omega dependence is more non-trivial, and it goes as a product of this product runs from however many cartons of the SOD, so roughly d over 2 of them, of the chemical potentials you have in the Lorentz group. The third term is temperature to d-1 with some coefficient f. Then there's a number which we computed, this C1, which is this Einstein term from temperature to the d-3. Again, this T scaling is from dimensional analysis because this has two derivatives. And same with the Maxwell term. And then there's a term that goes as omega squared with the angular potentials turned on. And the errors here are temperature to the d-5. Because these errors come from some four derivative terms that we've suppressed here. So if you want to read off the density of states, you just take the inverse Laplace transform of this. But let me point out some kind of nice features already that we can see. The first is that in 2 dimensions, all of these numbers vanish. There's a d-2 prefactor multiplying them. And first we recovered the usual Carty, the usual S transform of the Carty low temperature phase in 2 dimensions. The second thing is we notice that there's a divergence when omega is at plus or minus I. So that's a feature, not a bug. And the reason is that if omega is I, then states where the Hamiltonian or the dilatation minus the spin being a constant don't have any Boltzmann suppression, right? So states that go off to asymptotically large spin but fixed twist don't have the same Boltzmann suppression. And it's known that there are always infinitely many of these states in a CFT. These are these so-called Regge trajectories, and sort of these are the states that just barely obey the unitary bound, which is always roughly delta is bigger than J. So the fact that there are poles at omega equals I is kind of this formula rediscovering the unitary bound in some sense.
Can you read off the number of trajectories?
No, I don't know how to do that. You mean like in terms of like how many like what the lowest, the first lowest twist operator is? No, and in fact, I'll say more about this later. But this formula actually won't be, in order to really trust the density of states, which is how you would read it off. It turns out that the saddle will need that the twist scales at least with the square root of the spin. So somehow this cannot access the light cone regime. Well, I'll say more of this later.
Actually, I'm having still confused that philosophy. This is a small t expansion at the end.
A large T expansion.
Large T.
Yeah,
Sorry,
small beta,
large
large T,
expansion.
large T. So it's
Okay,
expansion of one over
it's
T.
all perturbative here. Then.
I'm sorry.
So it's all computable perturbatively, the original theory.
Yeah, this yeah, that's right. This is a large T.
Excellent.
Or expansion 1 over T. Although the third thing that already I find non-trivial is that in the absence of a gravitational anomaly, this predicts that the expansion is in the powers of 1 over T squared, because you can't make any term with an odd number of derivatives in this thermal effective action. And already, like just from a CFT perspective, if you told me that the expansion of the partition function at large T, of the log of the partition function at large T, is always in 1 over T squared, like that doesn't seem like completely obvious how to prove to me.
Well, that's the statement that's even true in QFT.
Yeah.
It's also
And
behind
the
fact-
shape in this of this omega dependence is also not true.
It's also behind the fact that the entanglement entropy skips goes into down by, L to the d-1, L to the d-3.
You're saying this is secretly the same fact?
Yeah, you write down a effective action for the method.
Okay, yeah.
And it has good
Yeah,
derivatives.
then it's the same fact, yeah. So let me write down the final thing that I promised before moving on to discussion, which is actually taking the density of states. And I'll do this for a 3D CFT.
A bit more about why this is not capturing Reggie trajectories.
Yeah, I'll say that in a moment, when I discuss this density of states. Basically, the answer is that when we take this inverse Laplace transform, we have to do a saddle point analysis, and we only trust our answer for the density if the saddle is at large temperature, because this is a large temperature expansion, and it turns out that'll force the twist to grow at least with square root of the spin. So here's the answer. So here I wrote them the primary operators. So I decompose in terms of the characters. In 3D, there's just one spin. The SO3 is just one dimensional per time. And the answer is something like this. So the leading term comes from the cosmological constant, and there's some one loop determinants you can compute. And indeed, this scales roughly as delta to the 2/3, as you would get from dimensional analysis. And then there's some leading terms from the Einstein and Maxwell term that roughly speaking scale like delta to the 0, although it's a little bit subtle how you scale the spin with the dimension. Which I'll say more about later. But this already now gives you some sort of given some delta, it tells you how the different spins are distributed. It's kind of like a statistics of the spins. It's kind of like a spin statistics theorem, you might say, for CFTs, but somehow that name was taken. Now I'll also let go. So maybe now I'll talk about the regime of actually, okay, maybe first I'll make a side comment about this leading term F. So this leading term, well, all of these terms are kind of like the central charge, but this leading term F is maybe most analogous to the central charge, because at very high energies is what controls the coefficient in front of the entropy of these states. And in 2D, there's a famous C theorem where the central charge always decreases when you go from the UV to the IR. And I just want to make a comment that that's not true for this value F. In fact, there are known cases where under marginal deformation, F will change, which doesn't happen with C. And under relevant deformation, there are also some cases where F increases. So for example, in the 90s, Dogsler, Klebanov, and Pete showed that this F changes by a factor of 3/4 when you go from the free point to the strong atomic point in n equal 4 super Young Mills. And also, Sashchev showed in the 90s that there's an RG flow from the Owen model at large n to a Goldstone phase of n-1 free scalars. And if n is large enough, this coefficient F will actually increase by a factor of 5/4 at large n. The only reason I point this out is that I remember, like in grad school, people would often say the following about the central charge in 2D CFTs. They would say this, they would say, oh, C is like a rough count of the number of degrees of freedom, because one, it decreases under RG flow, and two, it's the coefficient in front of Hardy's formula, which controls the density of states. And both of these facts are true, but the fact that they're linked to each other is just an accident of 2D. It doesn't hold in higher D. So this is not necessarily monotonic under RG flow. Okay, so now I'm going to talk about the regime of validity of this formula, which will be related to these questions about Reggie trajectories that Emil and Luca asked, unless there are any questions.
You remind me the thing that actually decreases under G, it does not appear anywhere here.
No, it's here.
Say it one more time.
The thing that does decrease
A
under G.
in 4D.
Yeah, so where is it here?
Oh, this will be related to determine the Weyl anomaly. So it'll be related to some Casimir energy shift, but it doesn't appear in these. Like none of these coefficients are obviously related to like A or C.
Yeah, it's just
or F.
referring to the top equation up there, in the top where the S thing.
Right there. Yeah, it'll be related to this Weyl anomaly.
Okay, but it's not in the.
No, it's not in the density of states. Okay, So what's the regime of validity of this formula? Well, to take this formula, we had to do an inverse Laplace transform, and we had to get some saddle in T and omega. And the thing that you need is that the saddle in T is large, right? It's parametrically large. If the saddle in T is not parametrically large, then you can't trust this this high temperature expansion. And I'll just say what happens when the dust settles.
So it's a saddle in temperature?
Yeah, that's right. In temperature.
But a CFT at any temperature is the same as at large
Compared to
temperature,
the
right?
radius of this.
That's right, compared to the radius, compared to the radius of the d minus. Right, this is an expansion 1/t, so we need to make sure this t is large. So in d equals 2, this is the famous calculation that Carty did, and what you get is that you need, I'll write delta, I'll assume j is positive, so you need that. Too excited. You need that the twist, the delta minus j, which is maybe h or h bar in 2D language, the eigenvalues of the L0 eigenvalue. You need that delta minus j is much larger than the central charge. But in higher than 2D, when you do this calculation, you actually get this condition instead. The delta minus j is much larger than the square root of f times delta. I'm assuming I'm just turning on one spin. In higher, like if in 4D or higher, there are multiple spins you can turn on, and if I turn on both of them, it's slightly changed, but let's just turn on one stochasticity for simplicity. And this is, in short, is why you cannot get the Regge trajectories at asymptote to fixed twist. Those will have some well, the formula might be universal, like maybe it's similar to, it's expected that it's similar to that of mean field theory, but you can read it off from a thermal effective action. But I actually think the scaling is quite interesting.
So, but this still allows you to, because you made a point that you're happy to reproduce the omega equals I singularity.
Yeah.
So when you're, let's say, close to saturating that bound, I guess omega is already very close to I.
Yes, that's true.
This expansion is log rho, right?
Oh, thank you. Yeah, very good. Thank you. Absolutely, very good question. Yeah.
So, but, I mean, Regge trajectories are like some sort of collective phenomenon. So is there some kind of collective mode that you can add to your effective action that?
Yeah, maybe. We actually thought a little bit about this, like maybe instead of compactifying in a circle, like if you try to look at some null direction or something, you can compactify it. And there were some papers by, well, I don't have much to say about that. There were some papers by Aldai and Aldacena that looked at this. I think that it might be interesting because I actually do expect that some of these Regge trajectories are universal. Like even in, I think, 3D easing model, like a lot of these Regge trajectories that they at high spin that they look at look very similar to behavior from like mean field theory. So given that we think for other reasons they may be universal for interacting theories, maybe there's another way to approach them.
On the other hand, it's also highly non-universal because it depends on all your spectrum of light operators.
That's right. That's true. But the functional form I think should be universal. There should just be some combinatorics of like the number of words and letters you can form from these light operators. So yeah. I don't have much more to say other than that. For this technique, this is what we need for the quantum numbers. But actually, I want to now talk. Well, okay. So we have this expression for the vector field theory, and we check this in various examples. So one thing you can look at is free theories, and actually there's a very nice paper by Kutuzov and Larson from the 2000s where they did something where they looked at these as well. For free theories, it's a little bit subtle because there's a gapless sector, but you can compute it, or you can do something like you put a Z2 twist to kill it, and it matches. It matches. But I want to talk about holographic theories, because then this condition will pop up again, and I think it's kind of interesting. So for holographic theories, we can also get the leading term for this entropy just by looking at the thermodynamics of per black holes in ADS, like ADS 4 or whatever. And the functional form fits precisely what we predict. And I'll even write down what the Wilson coefficients are. So for holographic theories, There's some order one coefficients that don't really matter. So they're all the leading order in expansion proportional to LADS over G Newton. So this is kind of like a some higher dimensional version of Brown-Peano. I don't mean anything about an asymptotic algebra at infinity, but just in terms of these Wilson coefficients being related to the radius of curvature of the ADS space. And of course, there are corrections. There could be corrections like from alpha prime or G Newton or whatever. But this is the leading classical the value from GR. And already one kind of interesting thing is that this means that for holographic theories, these ratios are universal, right? At least to leading order. And these ratios are not universal for any large n theory. Like I can take a large n, like n free scalars or ON model or whatever, and they won't have this ratio. So for a theory where like you can tune it, like maybe like n equals 4 super m mils or something, like at the free point, it won't have this, the ratio of whatever order one number that you get. But somehow as you then dial the strong coupling, you get the holographic point. All of these ratios of these Wilson coefficients must be whatever order one numbers that we calculate, which is kind of I think it's kind of an interesting test of holography.
So what do you mean by holographic theory? Is there a specific assumption you're making on your CFT?
Yeah, that's it. I assume the theory is well described by Einstein gravity.
Okay.
And this computation is just a GR computation from using black hole thermodynamics. But the other point I wanted to talk about for holographic theories is that per black holes in ADS-D for d bigger than 3 are unstable if they're spinning too fast. So this was, well, this was written nicely in paper by Cardoza and Diaz in 2004. So it's not that long ago, actually. And in particular, they showed the following. If the energy or mass of the black hole minus the spin in ADS units is bigger than some order one number that they computed, but I'm not going to write them. No. I'm going to write capital D this. If the black hole is spinning too fast, such that the roughly the twist of the black hole is larger than the square root of the energy, then the black hole is unstable. In fact, there was actually a very recent interesting paper by Mewala and Kim and others where they discuss what the endpoint of this radiation is. But the point I want to make is that this is very, very similar to the condition we wrote down here on the CFT side. And in fact, the powers of G Newton are also matched, right? F goes as powers of 1 over G Newton, so square root of F goes as G Newton to the minus 1/2 power. And our formula is trustworthy when this twist is much larger than this combination. And the black holes are stable when it's the same combination, but there's an order 1 number in front. And I want to say that this is actually very, very reminiscent to what happens in the case of ADS3 CFT2. For those who are familiar with it, and for those who are not, I will review it very, very briefly. How's the visibility? Is the erasing a bunch of times is still visible? Yeah, the question.
This instability is like a thermodynamic instability.
Yeah, it's like they call this a super radiant instability. So if it spins too quickly, yeah, there are states with more entropy that it would like to decay to. So in the case of ADS3 CFT2, there's a very similar analogy where the Carnot formula is valid when delta minus J is much greater than C. But the black holes form when delta minus J is on the order of C. And in D bigger than 2, well, the analog of this Carnot formula is valid when delta minus J is much bigger than square root of F delta, and the black holes are stable when delta is bigger than delta with this squiggle, because there's an order 1 number. And in TIG, actually, Hartman, Hiller, and Soika proved that if the spectrum if the light spectrum is sufficiently sparse, which they define properly, then the Carty regime, then the Carty regime extends, meaning that there's an extended regime of validity of Carty's formula. You can trust it all the way down to roughly the BTZ stability threshold. There's some funny factors of 2 that then let's not worry about. They proved it using modular inference, which obviously we don't have. But I think a very natural conjecture is that something like sparseness, maybe some notion of some holographic nature, will make our effective field theory have an extended regime validity, not just when you're parametrically larger than square root of this parameter f times the dimension, but you know, within some order 1 coefficient. I don't know how to prove it, but I think this is like an interesting thing to explore.
So, let's see, in the case of AES3, I know one of the kinds of things that can go wrong is that the way the system is that your assumption that you're looking at a single object breaks down. So for instance,
Like a multi-center.
yeah, that you're trying to dump a lot of angular momentum out of the system. So it says, okay, I'd like some kind of something spinning around that doesn't have much entropy, leaving behind something that's not spinning that has a lot of entropy. So is something similar happening also in?
Even for this instability?
Yeah, what is it unstable to?
Yeah, so there was a proposal recently by Minwala and Kim and others. I don't remember what it was on this gravity side. This paper is called like gray galaxies. On the CFT side, they wanted to say something like, most of the states here are not primary operators, but some descendants of some operator of much less spin, where you act with, you know, some derivative operator a bunch of times, and the original thing you acted on had a high enough entropy that it was larger than that of the black hole. So it could be related, but I would, you know, I have to look at it a bit more to give a more definite answer.
But you know it has to break down to give way to the rigid trajectories, right? So that's why you can't.
That's right. Yeah, indeed. We know that once this is constant, once this scales like an order, like it doesn't scale with delta, but it's just an order 1 number, and we go to large spin, then we know from, you know, Lycon bootstrap arguments or whatever of Komargodsky and Fitzpatrick and Smith and all that indeed they're not described by these black holes, but they're described by these multi-particle states. So something has to give. In fact, it would also be interesting to like, well, I guess I erased the formula, but somehow, you know, we need to glue this black hole formula to the formula of these multi-particle states that from Lycon bootstrap. And an interesting question, I think, is like, is this gluing universal or not, or is it very theory dependent? Like, imagine you take some family of operators whose twist scales is like delta to the 1/4, for example. This is somewhere in between these Reggie limits and these black hole limits, and like, is that universal? Is that theory dependent? Like, I don't know.
Sorry, can
Yeah, please.
I'm just a little bit confused. In the second line that you're saying black hole, is
Yeah.
this inequality supposed to be just about when the black holes are unstable?
Yeah, when they're
give
stable,
you
yeah.
more
Yeah.
validity of the entropy?
When they're stable, yeah, when they're stable black holes.
Okay, but the semi-classical approximation for the entropy of the black hole, is it still valid in the same regime?
Yeah, so this regime that I wrote down here is where if the theory was holographic, you would expect that you can trust the semi-classical black hole regime. So
I thought it had
so
to
for
be much
holographic,
bigger, no?
what's that?
Doesn't it have to be much bigger?
So for any PMT Ising model, this you can trust.
No,
But-
for the black hole mass.
No, even if it's really an Einstein gravity theory and you have a large gap with C, once you're an order 1 number bigger than this, there's a precise order 1 number. Like for this one, I know it's C/6, which is like actually twice the mass of the stable black hole, but there's an order 1 number that's computable, and then you can trust the black hole entropy. Yeah, so I can point you a picture of a picture because they were by Hartman, Keller, and Stoic. That is. Well, it's actually older than that, but anyways. Okay, I'll make one more comment before I'm talking about switching gears and talking about another comment, which is okay, we did this for holographic theories. Of course, you can, and free theories, you can compute this for other theories like and one thing we did that's kind of fun is we numerically took the 3D Ising model, and you know there's these numerical bootstrap people have bootstrapped a bunch of operators, like the lightest 10 or 15 operators and you can just build a partition function out of them, and you can just fit this to the effective action. And you can get some pretty good estimates for the first term, this cosmological constant term F. And if somehow there was a better way of estimating these scaling dimensions, then maybe one could also get the higher derivative corrections. So the remaining part of my talk, I'm going to now ask the following question, which is, so far, we've computed.
So actually, one question.
Yeah, please.
For the 3D easing model, I guess you can just look at lattice data for the subleading corrections too, right? I mean, this is just equilibrium.
Yeah, but well, okay, what we did was we fit the bootstrap data and we got F and matched these Monte Carlo estimates for F within a few percent. But our fit for the higher derivative terms using the bootstrap data is so bad because like there just aren't enough operators.
Yeah, but Monte Carlo could probably.
Yeah, Monte Carlo could do it, but it would be nice to have like an independent check or something. But I actually don't know of a paper. I know of a paper where they computed it for F, but I don't know of a paper where they computed these higher derivative terms. Do you know of one?
No, yeah, I would
Okay.
guess.
There were some condensed matter papers from the 90s that computed this F. And
Yes.
we're able to reproduce this to some precision. But I don't know of these of the higher derivative terms.
So in the 2D case.
Yeah.
You know, you understand it from the black hole side, but from the CFT side, the way you understand it is this long string picture, right? That you know, sort of like typical model for this is the symmetric product CFT, where the reason why things extend all the way down to low twist is that there's some effective size of the spatial domain that the thing is living on.
So for symmetric, yeah, sorry, go ahead.
So my question is there some analogous picture for why, from the CFT side of things, that the validity of the formula extends so much further in the?
No, I don't know of one, but it would be interesting. But this symmetric product, you don't need to be at the strong coupled point for this long string picture, or you do? Because actually, even at zero coupling, the symmetric products will extend.
Yeah.
Yeah, okay.
Yeah, you don't need to be in any kind of gravity regime,
Okay,
you just
okay.
need to have
Yeah, okay.
that sort of dynamic.
Yeah, so indeed, like even some theories where like LADS and L string are comparable, you would have this extended regime. So maybe something will be true here too, like maybe, well, I don't know, maybe like n equals large Brownian mills without strong coupling. You'll already get this as long as n is large. That could be, but I don't have any long string picture or anything like that. So far we've computed this partition function, but actually it was important that it wasn't spinning too fast. These omegas weren't too large, meaning omega could not be order 1 over beta. So this we could compute. But now, what if beta omega is an order 1 number? So what that means is, I'll give an example, which is, now I would like to compute, what about something like this? Compute the partition function again, but insert something like -1 to the j. So really have the spin statistics. And of course, these two expressions are the same, where I just shift omega by like pi over beta. Right? But in fact, if omega scales like 1 over beta, this EFT approximation breaks down. Because you know we need to take the beta small limit. So the question now for the rest of the talk is I want to ask it is, can we compute this spin weighted partition? I'm going to call this Z spin of beta omega. And in 2D, we know how to compute this. In 2D, there's just a separate modular transformation acting on beta and omega that takes this to the vacuum state. So instead of acting with the S transform, which recall took tau to -1 over tau, we act with a different transform, which takes tau to something like this. This is a more complicated modular transform, and what this does is this soaks up this this space. And if you take this modular transform, you see a unique answer that Z in 2D goes as e to the it goes exactly like it did without this minus 1 to the j, but there's an extra factor of 1/4 in the denominator. Okay, so this partition function it behaves differently. It's much smaller in the small beta limit. Okay, and there's this factor of 1/4. And the question I want to ask is, can we generalize this to higher dimensions using some EFT techniques? Okay, the answer will still be yes, or generically yes. And the idea is the following, which is that the way that we compute this, like here's my ST minus 1, and here's my S1. So this is some cylinder. And I compute this trace, but there's this minus 1 to the j inserted. But that's the same as computing the path integral on this geometry, where I cut this theory in half artificially, and identify now this point with this point and this point with this point. So as I go around the S1, I rotate the ST minus 1 by a phase of pi. So if I can compute the path integral on this geometry, this is some like beta, and this is the same as computing this trace minus 1 to the j for the partition function. I'm going to call these two sides of the geometry the left side and the right side. And I'm going to write this geometry in a different way. I'm going to stack these on top of each other, but replace the identifications. So this geometry is the same as the following geometry. So let's put the left and the bottom. So now this point is identified with this point. Oh, I guess I put the left on this. Sorry, this point is identified with this point. And basically what happens is I identify this with this, and this with this. This with this. And now the length of the circle is 2 beta, and this is an ST minus 1 mod Z2. This mod Z2 will have some fixed points, some codimension 2 in D minus 1 fixed points. So there also will be a defect action that I can write down. But the point is now I'm going to then take this circle, beta very small, 2 beta very small, and now act with my thermal effective action on this geometry right here. So I'm going to say that I now take 2 beta to be very small, and again, imagine that I get a gapped massive quantum field theory. So the claim is that log of Z spin will equal. Previously, we had a volume from ST minus 1, but now it's ST minus 1 mod Z2. So there's an extra factor of 2. There's still the 1 plus omega squared term. And previously there was a temperature to the D minus 1. But now beta goes to 2 beta, which is the same as T goes to T over 2. So there's an extra factor of 2 to the D minus 1, which combined here is an extra factor of 2 to the D. The remaining terms in the effective action stay the same, and there's also a defect term that we can write down. This defect will depend on what the fixed points of this are. For example, if the CFT started in 3D, then I'm rotating in S2, so the fixed points are the north and the south pole. So this defect in 3D will start as temperature to the 0. In general, I think it'll start as T to the D minus 3. And you can write down an effective action for the defect. More generally, so we see now this 2 to the D reproduces this 1/4 in the case of D equals to 2. More generally, if we were to insert a factor of e to the 2 pi I p over q times j in 2D, you would do a more complicated modular transform. You basically do negative 1 over q tau minus 1, and you get a factor of 1 over q squared. And this effective filter argument, you would have to do a more complicated cutting and gluing procedure, but you would get a factor of q to the d in the denominator of the free energy. So this is a generalization of some more complicated SL2Z transform to d bigger than 2. Where the free energy now goes down by, well, a factor depending on q to the d.
Is it reasonable to assume that the defect action is also gapped?
That's our assumption, and we checked this in some free examples, but I think, again, you can make a genericity argument, but I don't have
What's the
anything better.
genericity argument in this case,
Mm,
that you checked it in free examples, or?
yeah, well, in for example, we. That's fair, that's fair, so, yeah, fair. These take the functional form that of this, write down, I guess the genericity argument is that generic field theories are gap. So there's no tuning involved here.
But you didn't start with the generic field theory.
In our example, we did not. But for this construction, we do.
Okay,
The
This
construction is
this is
general.
a question about whether a gapless theory, the CFT, generates a thermal mass generically. And well, I could buy that for,
Oh, I see. Yeah, I don't have a better answer than the one I gave. It's an assumption. I think I have a few minutes left, so maybe I'll just say one last kind of fun thing that'll end that, which is just for entertainment, which I will call journey to beta equals 0. So right now, we've now computed this partition function. So the beta comma omega for any rational angle beta times omega. So for beta omega, it's some rational angle value. We know what this is. So let's let the log. The log goes as t to the d minus 1 over 1 plus omega squared q to the d. Right. So just for fun, I want to now pick an irrational beta omega. Let's say, this is like pi or something. Maybe, and just divide by 2 pi. And ask what the behavior of this free energy is as you take the limit where you fix the angle to be some random irrational value and you take the beta to 0 limit. And what you have to do is you have to write whatever irrational angle you have, you can do what's called this continued fraction or approximation of it. Where, where it's sort of there are successively better and better rational numbers that approximate any irrational number. Like maybe you guys have seen like pi, you can approximate as 3 or like 22 over 7, or the next one is like whatever it is, but you sort of keep more and more terms in the denominator. And what happens is
this more than saying that rationals are dense in reals?
Sorry?
Is there something more in this statement than saying?
No, I think
rational numbers are dense in.
I don't think there's that much more to the statement. There's just a simple algorithm that, you can just read off what these integers are.
Okay.
And then truncate the sum. And these are sort of the best rational approximations of any irrational number, in this neighborhood. These are called continued fractions. You can read the Wikipedia article. It's kind of fun. What's kind of cool is that as beta gets smaller and smaller, it starts to notice that it's at an irrational number. So when beta is some small value, it might think that this fraction is just 3. So there's nothing going on. But then it goes smaller and smaller, and it notices that it has a denominator of 7. And so then it'll pick up a 7 to the d term here. And then it goes lower and lower, and it then might think that it has a denominator of 113, and so on and so on. So I'll plot what happens as you plot as a function of the temperature, log of c. What'll happen is first it'll grow as t to some d minus 1 with some number which is set by the first term in the continued fraction approximation. Then once you get to some intermediate regime, which is controlled by what the gaps are between these.
I don't understand this plot. This
Yeah.
is related to approximating pi or some irrational number.
Yeah.
But why is that? Why do you get to show that on one plot for
Yeah.
z of beta?
No, sorry. You're right. So what I'm doing is I'm computing z of beta, and I'm setting the angle that I'm computing the Fugassi's at to be pi. So what I'm computing is, let me say more clearly what I'm computing. This thing that I'm computing is log of z beta and beta omega is equal to, I'm computing trace e to the minus beta h plus I beta j, where this is like pi squared or e or whatever.
Okay.
Yes, sorry, it was not there. So if I just choose some random irrational number, there's not a good in 2 dimensions, there's no SL2Z transformation that will tell me what I take this to. Nonetheless, this is a perfectly well-defined function. As a function of
So omega is blowing up as you're increasing beta. As you're.
Well, yeah, if you want, but omega times beta is fixed.
Yeah, but so you're sourcing, you have a huge source for spin.
That-
Physically, does it mean anything? Is it sensible?
I think it's just kind of for fun, like it's a perfectly well-defined function, but I don't know, like, how you would ever like measure this. Yeah, the physics is it good, like, it's just sort of for fun. And what happens is this angle here, as you get to higher and higher temperatures, it notices more and more the successive rational approximations.
How do you see that?
This is just a guess, because we can't compute it in higher, but in 2 dimensions, you can compute this. And in 2 dimensions, what happens, it's kind of fun, you can take your favorite 2D CFT partition function like Ising model or whatever.
Well, I understand if you did a truncation, you could bring it back to
Yeah, that's right, but 2 dimensions, you can do this exactly, like you can just ask mathematically plot this, these theta functions at these angles.
Oh, I see.
And what happens is, it'll be linear for a while, with the slope corresponding to this, and then it'll oscillate a bit, and it'll be linear with a smaller slope. And it'll oscillate a bit and linear with yet a smaller slope, and so on. And it'll never asymptote to a constant because the fugacity that you're turning on is truly irrational. But as you go to higher and higher temperatures, this slope constantly decreases, but there are large regimes where it's linear because it gets tricked into thinking that the fugacity is a rational angle.
Is that something you know how to explain other than numerically?
Well, what I explained is just with this picture, which is just that somehow like as beta gets smaller and smaller, it thinks it's some rational angle, and so it obeys this.
What do you mean by it thinks it's some rational angle?
Well,
What actually do you mean by that, other
yeah,
than making
but-
this numerical plot?
What I mean is that in order for us to trust this formula, we don't just need beta to be much smaller than 1. We need basically q times beta to be much smaller than 1. So when beta is not yet on the order of 1/q in some term in the continued fraction truncation, then it doesn't know to have a smaller slope. So it's effectively, the chemical potential is effectively the truncated continued fraction. This is, I think, just kind of a fun thing that you can make possible. But I think I'll end the talk here and take questions. So thanks very much for your attention.
All questions, thank you.